Today we're going to be solving a very basic physics problem. Let's go ahead and understand the problem. A point particle is launched at a given initial magnitude of velocity at an unknown angle theta above the horizontal surface and travel a horizontal distance d. Find the angle theta. So if we draw out the problem, we know that there's a ball being launched assumed to be an Earth environment, so let's consider downward to be negative and upward to be positive. So we have a gravity and we have some distance d traveled once the ball lands back on the ground, and it will create this parabolic trajectory because the horizontal component of velocity would just be constant, and the y component of velocity would be dealing with a negative acceleration. So we can use this information to come up with two position equations to help us solve this problem. So let's go ahead and label this diagram before we begin. So as you can see, it's a lot more clear. We have a v naught here, a magnitude of initial velocity, as this vector indicates. We have some angle theta, and we have some horizontal distance d traveled once the ball lands back on the ground. So let's go ahead and work with two equations dealing with the x and y positions of this problem. So as you can see, I brought up two position equations that are relevant in this kinematics problem. They're really useful. They can be used a lot of times, and there's actually a much better notation than this, but because this is a beginner's problem, I'll just be using simple notation as these instead of vector form. So we have a given horizontal distance d, and we have some given initial magnitude of velocity. This means that we could either start with the x or the y, whichever is preferable to construct our equation to solve this problem. So these are fundamental equations. They may require some memorization, but there is a way to derive these. I will cover them in another video. But let's go ahead and start with the y equation. So some y position with respect to time is equal to negative g over 2t squared plus v naught y t plus y naught. So let's go ahead and look at this problem. We can do some replacements here. So once we launch the ball, we start at time equals 0. The ball gets launched at that instant. It travels, and falls back down on the ground. So after it falls back on the ground, there's some amount of time it took to go through the air. What that means is we can solve for that time with this equation over here. All we have to do is just replace the vertical position evaluated at the end of that time, which is y sub t, with 0 because it lands back on the ground. And y naught would be 0. What y initially starts at 0 because it starts off at the ground and ends up on the ground, so it should be 0. And as you can see, we have another unknown here, which is v naught y. That's only just the y component of the initial magnitude of velocity. If we do some trig over here, that just means v naught sine theta. So let's go ahead and make those replacements. Okay, as you can see, we have 0 equals negative g over 2t squared. This negative g is just the gravity, and we said downward is negative, so we just have it as negative g. Usually it will just be a over 2t squared, but in this case, our acceleration is just negative g. So we have 0 equals this whole thing, and we can actually use this to solve for the time it took in the air. So let's go ahead and do that. Let's move negative g over 2t squared to the other side by adding that on both sides. We would get this, and I could cancel a t out. It's not really good to do that, but I know one of the t's equals 0 because it starts off on the ground at t equals 0, so it makes sense for one of the t to equal 0. You can also just solve factoring, but I know one of the t's equals 0, so I can just go ahead and cancel it. And from here, we can just get our t, just do some basic algebra, and we'll get this. Now, What we could do with this information is we can go back over here, look at the horizontal position equation. As you can see, with that amount of time it took in the air and to fall back down, it travels a horizontal distance d. So x of t means that horizontal position that we evaluate within that amount of time. This time right here that we just solved for. So we know that just equals d. So let's go ahead and replace that with d. And from b naught x, we know that's just v naught cosine theta t. And x naught is obviously 0 because you start off at 0. Now we can go ahead and substitute in t, and we can actually use, if you notice here, we have a trig identity 2 sine theta cosine theta. We can rewrite that as sine 2 theta, and then we have v naught squared. We have it divided by g. And from here, we can just go ahead and do some basic algebra to solve for our theta. You would have to just multiply g on both sides, divide v naught squared by both sides, and sine inverse both sides, and divide 2 on both sides. It's a pretty hefty algebra process, but it's really simple. And here's the answer. If you're given values, then you can go ahead and do it symbolically first, as it's good practice.